Yeah, thank you so much. And as you already heard, the title was a little bit complicated to pronounce, and we lost that afterwards. But in short, what I'm going to focus in this talk is about reachability analysis, and this is something that probably many of you are hearing more and more in the SCA space. And with my presentation here, I want to sort of dig deep a little bit into what this topic is about, why it is relevant, and how does it actually work and compared to other existing technologies. So a little bit before going through the talk, it was good to give a little bit of introduction. So I'm a member of technical staff. I would say I'm more of a researcher than a developer. I'm not a 100% security researcher, but I know a little bit the high-level topics. And the big change from, of course, last week is that I have a PhD in this topic. So you can test me if I know everything about software supply chains. And if I'm not that good, then the committee members that I have last week didn't do a good job. And so what are my main interests? Well, I'm primarily interested in trying to scale program analysis techniques, and that particularly in the area of software supply chains. But also something that I'm also very interested in is to do empirical research and doing trend analysis around different ecosystems such as NPM, Rust, and others to understand a little bit what is going on there, developments, how are, contributions being made, and also a little bit, for example, what is the situation around the security of the infrastructure and such things. And before delving into the whole topic of reachability analysis, I like to rewind back in time, all the way back to 1980s, because it's always very nice to see what did we think about the whole notion about software reuse that is very, very evident today, and that is building a lot of our products and economy in general. And I was browsing online and found this very interesting document, or like a book from the US Department of Commerce back in 1986 that talks about software reuse, a little bit the ideas around it. And I found one particular interesting page and 2 paragraphs around it on what is sort of like the ideal or perfect software reuse scenario. So when we come to selecting third-party libraries, how should it be? Or how should, let's say, the work around software reuse be? And I really like the definition here. So, for example, the first one is reusing well-designed, well-developed, and well-documented software improves productivity and reduces software development time, costs, and risks. And the other one is around quality. Improvements in the quality of software developed from well-designed, well-tested, well-documented, reusable software components. And I think most of us agree that this is, what we're really looking into when we are trying to get something online, from downloading from NPM, what else, to using our products. And fast forward, how does, let's say, software reuse look today? Well, it is the package manager. And this is a little bit to just give a high-level idea. Why is it really such a great thing to have a package manager? Well, I see that there are basically 3 things. One thing is that you can essentially install any type of package, and most likely you will not have any type of dependency conflict. I think many of you have seen in many cases that you can use the same library, multiple versions, and it all just works beautifully in the software. The other thing is that there is a centralized distribution, which makes it very nice to essentially, of course, download packages, but also publish packages as well to share with others. And it is, of course, a nice gateway where you can get thousands of libraries and frameworks. And if you don't have any policies around what you can use and not use, this is a very nice way to immediately avoid reinventing the wheel many times. And this is essentially the manifestation of software reuse today. And it's all done in this simple command: package manager install library. But let's go a little bit deeper to when you run this command. And I did this for a Rust package some time ago. You think you're installing one package, but then what you actually see, it's easily coming up to in the numbers of 307, 500 in some cases. But it's always very interesting to see that you just declare on a package. For example, you might declare a package on accept, so body parser, But then there are like tons of other packages that are coming up. And what is very important here is that the ones that we are able to directly declare, the direct dependencies, those are the ones that we have control over. We can always change the version, we can remove that. But the ones that are declared in those packages, we cannot do much about it. There are, of course, in some languages mechanisms, like in the case of Maven or Java, where you can exclude transitive dependencies, but overall, you don't have much control over it. But you accept that you're using these packages, and they also have the same execution right as your own code and the direct dependencies. If you're not also pinning the versions, and I mean, I think today this is more of practice, but many years ago, especially like in NPM, there was sometimes debates whether you should use the caret range, tilde range, etc. But if you're not pinning versions, then you really like to have random updates in your build systems. And just to sort of give like a quick course on what it is, I think most of you have this experience. If you run this, you get these versions today, but let's say like I run a fresh build, a couple of days later, I get completely different versions. So you have this inconsistency here. And I think this is like very clear in general, but if you think in terms of, let's say, like DevOps practices in general, right? Whenever we do some type of integration, we always run through a lot of set of tests to ensure that this little change, whatever, actually passes our like quality marks in general. But when it comes to these updates, which are done in the package manager, we don't have those mechanisms to ensure that these changes are compatible with our system. Of course, there are tools like Dependabot, etc., that allows you to do this, but if you just think of the package manager as a tool itself, it doesn't really offer this functionality. And also, this is a little bit, I guess the researcher means like the popularity of packages, and as you can see, it keeps growing all the time, and that's also a little bit why we're seeing in when you're downloading one package that you're getting many more, because packages are essentially building blocks for many other new packages that we use. And reading the news, we always find these nice articles that, I think the most, in my time when I started this research, was really left-pad, and it was always maybe a little bit exaggerated that the whole internet broke because left-pad was deleted. And but there are, of course, a lot of other social engineering attacks, typo spotting, particularly in PyP repositories, where we constantly see this type of attacks in general. And then for any organization is that you learn about these vulnerabilities. Then, of course, within the security team, you have to start looking into the organization widely. The first question is to basically answer which projects, systems are actually using this particular vulnerable library. And one thing to note is that with these CVEs in general, we only know, let's say, like the version of the package, not necessarily exactly which type of source code in all cases. That is the one that is the, is basically the exploit. Then, of course, the other question is that, okay, it might be a vulnerability, but every organization, even projects, use a library in a very different way. So not all use cases may be risky in general. So there sort of comes like the other question, like, do this new exploit pose a risk to organization? And then once you have done like this whole process around first identifying where do we use this library, and do we have different use cases, do they matter in general? The next step comes the remediation steps, which is either you have to do something short term if you come to the conclusion that there's a very high severity around it, or there might be like a low severity depending on the outcome, which means like, you can maybe deal with it much later, or like do it later in a major update, for example. And then of course, the other step is what are, let's say, like the resources required to remediate this, right? I mean, if it's a major operation, in some cases it's almost impossible to update certain libraries. And in other cases, you might need to spend much more resources instead of doing feature development. There's always like this type of discussion, but what is like very interesting to me at least is that these are, let's say, like, I mean, very reasonable questions, but there are no easy answers to it. And this is also a little bit why I like this, like, as a research topic when I started many years ago. And looking at, let's say, like, at the toolbox that we have, there's of course the dependency checkers. There are tooling that allows you to analyze in the source code for certain code patterns of vulnerabilities, etc. Then there are, of course, the automated dependency updating tools that allow you to do the remediation, because when you run, let's say, like an update, you also do regression testing, and hopefully if there's no problems, you can immediately remediate vulnerabilities. In other cases, you will also have to resort to patching. But overall, if you look into the whole process of dealing vulnerability, there's a lot of manual effort, but the tools are not that, let's say, like, strong or helpful to answer this type of question. And particularly on the first one, dependency checker, that's something that I'm gonna little bit highlight a bit more, is that it seems like it's very easy to just run Maven dependency tree or npm dependency tree, and there you have the answer. But there is much more to that, which I will touch upon a little bit later. And yeah, so how does, like, the dependency checkers work, or which I will call reachability analysis 1.0? Typically, the starting scenarios that you, I mean, okay, I added license and update, but normally it would be a vulnerability. You go to the projects, let's say, like, you're scanning the organization. I mean, just to see, like, do you have, let's say, like, a library with this particular CV? You build a dependency tree, and then you can start seeing by scanning it. So it could be similar, like npm audits. You find that one package, like with the cross, is a vulnerability. Then another one has a license problem, and yeah, another one vulnerability. In the case of the dependency tree, you actually don't really need to do reachability analysis, because you will normally assume that you always use it. But here comes the part where you want to know, are you affected or impacted by it? That's, let's say, like, when you limit down the paths, right, to see that, okay, it's in this transitive dependency, now we need to spend manual time, are we really impacted by it or not? And, yeah, sorry.
So I have a question. Like, in this part, are you already speaking about if we are using any vulnerable methods? So, for example, if a specific vulnerable method is vulnerable on that package, is the package that is calling it using any of those vulnerable methods or not? Is that what you're talking about?
That's coming later. So you're very far ahead. I'm like coming slowly there.
Okay, sorry.
Starting from the beginning.
Okay, sorry.
But yeah, exactly. So yeah, so actually coming to that point. So here we're not looking at all at the source code. This is essentially your build manifest, the dependency descriptors, and this is, let's say, like your working scenario, right? You find that if you look at this picture here, this is the vulnerability, this is your direct dependency. You need to start putting manual effort here to see, I mean, you can, of course, run testing, etc., but to have maybe additional confidence, you have to sometimes manually look into, are we really exploited or not by it? I mean, it is nice to already, let's say, like, narrow down, but what we are seeing with the number of increasing vulnerabilities in general, you will find cases where you have maybe 500, 10, I don't know, 10, but like 500 findings or 1,000 findings. Even within EndoLab, we have some customer with, I don't know, or 1,000 findings, etc., just using this information. And I mean, how do you start prioritizing? It becomes very complicated. Yeah, exactly. This is sort of what I came into. That yeah, some libraries are not under control, which are the transitive dependencies. There can be hundreds of findings. Which one should I prioritize? So we of course learn that we are importing libraries with problems, but are they actually problematic for us in general? And this is often attributed as like an alert fatigue. I partly agree to it, but I think there's a more problematic issue here, which is more what is let's say like for social truth when we do this form of analysis. And the most important part is that when using this type of tooling, dependency descriptor is not source code. It doesn't really look into how we are actually using this type of dependencies. You can easily import a library and just import it or not even import it, and still it will make the alert that it's a vulnerable or problematic one. And imagine like having to look at this, having to attend to all this type of alerts that will make you pretty tired in general. And this is, let's say, like in general, when I would advocate, and something that I also did in my research, that whenever we come to dependency analysis, we have to start from the source code. The dependency descriptor gives some idea about what is declared, but it doesn't really tell what is used. So then comes the question, like, which is a little bit around the vulnerable functions. How can we understand how we are using software? If you use the SBOM tools, like software builds on materials, we can directly get an idea about what are the different package relationships. But then the actual reuse is what we see in the source code, and this is something that we need to start capturing. And as you can see here, it's like we have the same scenario. We have the application, the direct dependency, transitive dependency, and the same thing here. We start to get an idea about what are the different functions that are used in the app, and then obviously the dependencies. And then by trying to map how they are calling each other, we can get an approximation of what is being used, for example, from the application versus the how the library is used. Like basically, what are the APIs that are being invoked. So the whole idea is to essentially make source code as the first-class citizen. So you have your project dependencies, and by then moving to the call graphs, we can directly start understanding which components of dependencies are we actually using and not using. And this becomes important, and this is where the selective reachability analysis starts to have an impact. Because here, let's say, like we have like the JSON size that is a vulnerability, and the BAS function that is also another vulnerability. And exactly. In both cases, they are essentially this direct dependency calling this transitive one, but they are used a little bit differently. Yes, and then by doing, let's say, like the having the call graphs, this is something that we can have statically. You then want to do reachability analysis, and with the reachability analysis, you actually do it like reverse backwards. You start with the vulnerability, and then trace upwards, and you will find that in the case of BAS, there is some path all the way up to the project. But for this other one here, we can see that like our main application doesn't actually call this other public API, only uses the stats_JSON API. So there's no path to, let's say, like this vulnerability, which means that we can directly dismiss it. So we find that JSON_size is not reachable and it's not impacting, but on the other hand, the other one is reachable, which means we should start spending a bit more time to look into whether it is an exploit or not, because now we have a little bit more evidence around what might be used and not used. And this is essentially like the whole idea around reachability analysis. I hope it was clear or not. Okay. Yeah, just ask questions in case something is unclear. All right. So introducing this. So where does this like call-based reachability analysis make the most difference compared to what is currently out there? There are three areas that doing source code analysis actually have an impact. That is around transitive dependencies. The other one is phantom dependencies, and then dependency updates. And coming to transitive dependencies, and now there's a way for me to quiz people. How many dependencies does app version 1 use?
How many dependencies?
Yeah, how many dependencies? So, yeah.
2.
2 dependencies.
Yeah.
One?
One dependency.
No, 2.
Okay, so one is saying 1 dependency. I'm curious.
Dependency is the library. Is it the library dependency?
Yeah, these are the library dependencies. So this is the application, and these are, let's say, like the dependencies.
So you've got 3 libraries.
Exactly.
It only depends on the first 2. The second one is unused.
Yeah, exactly. So if you would use a normal dependency checker, it will tell you you're using 3 libraries. But in practice, you're only using 2 of them. Yeah, and it's very clearly seen here that if you have this function in the lib to call unused, you're not in any way through, let's say, like the application via lib1 calling this function. And this function only calls library 3. So you can completely dismiss anything that's happening in library 3 here.
Can you build your app without library 3?
That's a more tricky question, because if you're importing, for example, interfaces, data structures, then that affects it. But if you look at, let's say, like the binary compatibility, I know, for example, in the case of Rust, it actually strips out all the code that you're not using. But in the case of Java, I'm not fully sure, because sometimes there might be interfaces or implementations that you could potentially use. And this is sort of highlight that context is king, because what we're doing here by introducing how we're using code, we're actually now providing context to how we're using dependencies. Because with the other perspective, we don't have any context. We're not really bothering about how does the end user, how does projects use their dependencies. Because with the non-code-based reachability analysis, what we are saying is that whenever we run this analysis, we are assuming that all code of the direct dependencies are used, and then that the whole code of the transitive dependencies are used. So that's a very important thing to note when thinking about non-code-based dependency checkers or tooling in general. And so I did a bit studies on around the Rust ecosystem, looking into what you use, what I exactly pointed out before. One is using the code-based representation, like with the call graph, how many dependencies are using, and one is just using the regular package-based one. So let's say like the one that's called test is the call-based one, and the traits.io is the one that is basically using only package information. And I was essentially every month compiling a call graph version of the whole ecosystem. And I was very curious to see, is there like any major difference between when it comes to looking at number of dependencies? And what this really gives us an idea is that if you're not using a code-based analysis tool, does this like your non-code-based analysis tool, approximate what you're using or not? And what was very interesting here is that overall, there is, let's say, like if you look into the average, that the numbers are much lower for the call-based representation when you count number of dependencies per project. But then when you look at the overall median, or actually in general, you will find that they approximate pretty well. So, if you want to, let's say, like counting, let's say, like number of dependencies or tooling that doesn't really, where you don't really say like prioritization per se. If you know there is a vulnerability in a direct dependency, and you're not necessarily like using fancy call-based, most likely it is the case that it's a vulnerability. But the situation changes quite drastically when it comes to transitive dependencies, because what we find here is that there's a big gap between how many number of transitive dependencies you are using versus the number of transitive dependencies that are declared. So here, what we found is that, for example, we had like one snapshot of the create repository in February 2020. We found that on average you would find 17 transitive dependencies, whereas when you use the code-based one, only 6 of them. And this is attributed to what I was showing earlier, that everyone is using their projects very differently. I mean, if you are having a parsing library, and you might offer JSON functionality parsing and XML parsing, you're probably only using the JSON one. Whereas like the XML one might also have some other underlying dependencies which are not being used. So this really matters quite a lot. And then another, which is my new favorite topic, which are phantom dependencies. And sometimes in dependencies, actually not sometimes, but I think I've seen it only in one case, you find this very interesting commands that does pip install pandas or something else. And yeah, just to ask, what is the problem with this if you do using a dependency checker?
It's not in a dependency file.
Exactly. Exactly. If you run dependency checker, you will not find this. So how will you know? I mean, if you want to go back to the question of asking, like, are we actually using this library, right? If I run the dependency checker, I wouldn't even know that we are using pandas, right? So this is why it's important to do this type of, for example, code-based analysis or source code analysis to complement what's available in package information. And then another topic, which is also, you can say, I like to cite my own papers here, on third-party library updates. And this is around are tests in general reliable for updates? And I was like very just curious in general. One thing I just wanted to know, since like when we use dependencies in general, I mean, I don't have like too much developer experience, but at least like my idea when it comes to testing is that we focus a lot of testing around our own application. And when we use third-party components, we use it for the ergonomics, so we may not really test it that much. But then there's also the other problem that sometimes, especially with database drivers, we might do a lot of mocking. So if you run the select regression test on that, you might not be able to test the functionality of changes. So this is more around the, let's say, like the remediation step when you want to update something. So I just developed like a very simple approach that is also based on reachability analysis, where you first try to find out, similar to the vulnerable functions, what are the functions that are changed. Then you do the same call graph integration and then the reachability analysis. And the sort of idea here is that when it comes to dependencies, we don't have test coverage for all the dependencies we use. For some we might have, but for some others we don't have. And having reachability analysis might be a way to complement that. And I did this on open source GitHub projects. So what I did here was essentially doing dynamic call graph integration. So what I did is that I traced, let's say, like first I statically extracted what are all the functions that I see from, let's say, like in your project, what are the ones that you are calling in to dependencies, and I checked, do you actually have a coverage statement or not? And I find for like the direct dependencies, we're about 60%, and 40% is uncovered. And then for the call graphs, the transitive ones, it was 20%. But as you can see, I put a warning triangle because this is just an approximation. So I'm using call graphs, they're not like extremely precise because there might be a bit more sound, which means that they could also be missing things as well. But then when I try to use my approach here, and I call this uppdatera, which means update in Swedish. So what I did here was that for a subset of the project, I used essentially mutation testing here. And with mutation testing, what you do is that you're basically trying to mutate, for example, a plus value to a minus value in the project, and your test should be able to detect that. But what I did here is that I did this for the third-party dependencies instead. So I didn't, let's say, mutate, let's say, like all the functions of dependencies. I only did for the ones that were reachable from the tests of the project. So if you have, let's say, like 5 APIs of the library, the ones that you test reach might be 3 of them. I only mutated those 3 ones. Just to see whether the test is able to detect those artificial regressions. And I find that on average, around 30% of the tests were able to detect this. And using a static analysis tool, I was able to take 72% here instead. But it's important to note that when you start using whole graphs or static analysis, there will be false positives. But what was like the important thing I want to highlight is that there's a need for maybe having a hybrid approach. So interestingly, when I tried to publish this article around this, I got this comment that why are you including logging libraries, because they are not that important, for example, compared to the Spring framework, etc. It's like you should exclude that from your result, because why would you even bother about update or changes to libraries? But I think now many of you know about Log4Shell. So since reviewers are anonymous, it would be very nice to just message him that this is indeed important. A little bit, the main thing I want to highlight is that, it's important. So what I feel like it's important for when it comes to tooling around third-party library updates, what I feel is really missing is some confidence level, because if you're updating a component and you don't have enough test coverage, I think that's very important to have that information. And when you don't have this information, that's where you can complement something with reachability analysis, because with the core graphs, you can at least see if there's a path or not to those affected functions that are changed. And I don't know how I'm doing time-wise, but So we're gonna be less like at the OWASP Global AppSec, and we're gonna have a happy hour. Location is still to be determined. And for those who want to try out what we have at Endo Labs, which is built around a lot around the technology that I've been mentioning, for example, around phantom dependencies, we have a free trial, so feel free to try it out, and also give us feedback as well. That's also very nice. And then, should I go to the last slide, or maybe can I have some QA first?
Is that your last one?
Yeah, and then
No.